What's up, Chuck? Hey, Jack. Hi, Andrew. Can you write my literature review for me? I probably could. What's it on? And how much are you going to pay me? Differences in the way men handle depression versus women. And I got like $3 in my wallet. How long's the paper? 7 pages. It's not $3. Is there a practice test that we can follow along with? Yeah, so there's the practice test in on campus. If you go to our on campus page and it's in chapter one topics, and then there's three practice tests there, and that's in order. I have it here as well, but it's the one I gave you in class. And if I need to, I'll regenerate a couple more questions so we can see it. Donation link? Not yet. I think you actually have to like have a lot of people watch you, and I don't, because I'm a math YouTube channel. Thanks, Daniel. How do I gift subs? Just pay me cash. That's fine. No emotes, no emotes. I'm gonna. This is gonna take more time if I keep responding, so I'm just gonna keep writing. There's really not a whole lot to write. It's just it feels like there is. GG does mean good game. I don't know what else that would mean. 100 pounds of food tomorrow for 100%, right? That's what he told me. Um, no, no, I may have said that, but I take it back. We don't actually need 100 pounds because we're already going to win. Rice. I'm good. I had a freshman bring in like 150 pounds of rice, and I'm like, dude, I love it, but I can't take it. It'd be great. Like I get the thought. It's easy and it's kind of cheap, but I don't know. I mean, like we're giving food out to people, If I was like really hungry on the streets, that'd be like the last thing I want. Gaming stream over Thanksgiving break, maybe. We'll see if I have a like I'm really behind in grad school, so there's that. At some point, maybe. Okay, I feel like me writing this is going to be kind of useless because this is just a bunch of like it's the same thing over and over again, and I'm hoping we kind of see that. There's a little bit of a continuity that I could write up here, but I'm not. I don't know. No test tomorrow, so you can catch up on grad school homework. I need more than just like your hour of class time, and I had kind of have to like it's programming stuff, so I need to like I really can't have. I need to actually be able to think. So no, we're still gonna have the test. No, he just needs to manage his time. Yes, you are right. That's more along the lines. So I'm just gonna do this. I need to get my other stylus. Um, so I did. These are some notes, but I think. Oh no. But I think that most of this stuff is just it's the same thing. So if we understand these concepts, that's really what I'm worried about. And most of it has to do with dividing out and rationalizing and all that stuff. There's a little bit about continuity, which we'll talk about as we get there. But I feel like it's just going to be better if I just like kind of go through this. So normally what I would do is I would condense a bunch of notes, which I'm already late on, and then we would do the test. I'm just going to do the test because I think that's going to be better. So throughout this test, I'm going to be asking you to evaluate limits. That's pretty much it. Right, a whole bunch of limits and things about limits and continuity and more limits and then more limits. That has to do with asymptotes and then more limits, right? So this is really just a bunch of, it's a limit test, right? So everything we did on the quiz a while ago is that but extended, right? So first set of directions says to evaluate each limit by constructing a table of values and approximating from left and the right. So this gets into the definition, right? So the definition says that basically, this isn't the exact definition. We wrote down the exact definition, but I'm not worried that you know it. But the definition kind of says that as you get really, really close to some value, the limit is what's happening in between, right? So if you're approaching from the right and the left, it's what's happening as you get infinitely close with those 2 points. Okay, so by this question, right, I'm asking you to construct a set of a table so we have x We have y. Okay, and we're just plugging in numbers really close to our limit. So that says x equals -2. It's probably too small on your screen, so I'm going to erase that. So we want to approach from the right. So let's say we start at like -2.5. Sorry, -1.5. That's on the right. And basically, we're just going to plug this in, and then we're going to get really close. So if we plug this into a calculator, this -1.5, again, you can store these values and just kind of keep repeating it. So I'm going to do -1.5 stow x, and then I'm just going to type out that equation. Okay, so x squared plus 2x divided by x plus 2. Keep in mind that when you're writing this in a calculator, your numerator and denominator should have parentheses around it, because if you don't, it won't work the way you want it to. All right, so when I do that, I get -1.5 out, which I didn't think would happen. So let's get closer. Let's go to like -1.9. So when we plug -1.9 in, -1.9 stow x, we get -1.9. And then let's get a little bit closer. And we get -1.99. Okay, so that's from the left. And then we're going to have our -2. And then we're going to kind of do the same thing on the left. Sorry, this is on the right. So let's do like -2.001. And when we plug in -2.001, if we just plug that back into our equation, we also get -2.001. Right, so I think the reason this happens is because, right, there's common factors here and you're just left with x. Okay, so analytically, we should be able to get that we're just, the thing we're plugging in, we're going to get out. Okay, but what I'm asking you to do in this question is to construct this this table of values. And then basically we're estimating the limit based off of these two values right here. Right, so what's in between -1.99 and 2.001? Well, it's 2. It's -2. And then that'd be our answer. Right, so there's a lot of different ways you could do this. You could also just kind of plug it in, but then you would get something that looks indeterminate. But yeah. Do these save? Like, can I watch these later? Yes, you should be able to watch these later. I think I learned how to actually make that happen. And it's been working, so yes. So number 2, same thing. We're plugging in values really close to -2. All right, so let's do like -1.9. And then we're plugging it into -x plus 2, all divided by x squared plus x minus 2. And when you do that, we get like 0.33. Let's get a little bit closer. So like -1.99. If we plug that in, you get 0.334. Then we're going to have our limit, which we don't know what happens. And then we're going to be like negative 2.001. And we get like 0.3332. Okay, so I think this is going to a third. So it's going to go to 0.33 repeating. I want to double check that though. So there should be a 2 after this, and then negative 2.001. There's a bunch of 2s, so I actually want to see what this goes to. Yeah, it's going into negative 1/3. That's right. Okay, so again, we're estimating it based off of these 2 values. You can use that analytic stuff to help, like I am, but it's really just we're plugging in a bunch of numbers and seeing what's happening in between them. Okay, so that's numbers 1 and 2. This is like the first thing we did. Expand the limit as much as possible, then evaluate. So this has to do with the properties of limits. So the properties of limits basically just say we can split things up. And maybe I should write these. So properties of limits. We'll start with the sum and difference. So this says that the limit as x approaches c of f of x plus g of x. Right, if we have a limit of a sum, this is the same thing as the sum of the limits. So we have the limit as x approaches c of f of x plus the limit as x approaches c of g of x. It is not the same thing. On the test, would you like us to change the decimal answers to fractions like 1/3, or do you not really care? Like, I think your final answer should always look like a nice fraction, because I'm going to give you something that kind of cancels out. Right, so if you look at this, you should be able to do this analytically using dividing out or rationalizing. Okay, so really you should get 1 over something, or something over 1, or something like that. So the negative 1/3, like if you're, yeah, I'm kind of expecting a fraction here. Product and quotient work the same way. So of limit of f of x times g of x. So if we have a limit of products, we have the product of limits. And we pretty much just have this pattern. The other's like scale factor. So if we have a limit, these are way out of order. These are in your notes. So if we have the limit as x approaches c of like some number, c is probably not good to use. We'll say b times f of x. Then we really have b times the limit. Same thing with quotient. So if we have a limit of quotients, sorry, if we have a quotient of a limit, no, if we have a limit of a quotient, we can take the limit, we can take the quotient of limits. That took me a while. Let's just write these down. There's no harm in it. The only thing different here is that g of x can't be 0. Sorry, g of c can't be 0. And then the last one is the power rule. I think that's it. So if we have a limit of a power, we have the power of a limit. So basically, every single operation that you guys know can be broken down into its simplest pieces, right? The only thing I'm missing up here is the limit of a constant. The limit of a constant is just the constant, though. Okay, so I'm going to have these over here so we can see them, and we're going to rewrite these things. So the limit as x approaches -3 of negative cube root of 2x plus 3. We can rewrite that as, first of all, the negative limit as x approaches -3 of the cube root of 2x plus 3. Right, so this negative is like a constant, so we can move it out front. Then we have a power, right? So whenever we see like cube root, this is the same thing as something to the 1/3. So we can say the limit, the negative limit as x approaches -3 of 2x plus 3 to the 1/3. And then we can say that this is the negative limit as x approaches -3 of 2x plus the limit as x approaches -3 of 3 all to the 1/3. Right, so I'm going to kind of stop for a second. First thing we did is we took out the negative because that's like a constant. And then we rewrote it in terms of a power, right? So we're taking everything to the 1/3 power here, and that's moving outside. Okay. Then we're splitting up this sum into 2x and 3. And then we can do one more step, which says that we can take this constant out. So then we have -2 times the limit as x approaches -3 of x plus the limit as x approaches -3 of 3, everything to the 1/3. Okay, and that would be our kind of our final answer. Probably not going to give you a square root. That's just like really tedious. Maybe. I'm not going to say I'm not going to, but that's what we would do. I might make it a couple steps shorter than that, but and you don't have to show all these steps. This is just like I want to show you what's being done, right? So we're taking the constant out, right? The negative goes out first. Then we're worried about the cube root, so that goes outside. Then we have a limit of a sum on the inside of this, and then we have the limit of a constant factor, and then we're done. Okay, so that's tedious, but that's what we would do. Okay, number 4, kind of the same thing. We can split it up into a quotient first. And this is not, okay, it is asking you to evaluate. So this would be -2 times -3, which is -6, plus 3 to the 1/3. So this is going to be this. Okay. Yes. Okay, and then you can split this up further. So we have the limit as x approaches -2 of x squared minus the limit as x approaches -2 of 1 And then the last thing we can do is we can take this power and put it outside. So this would be the limit as x approaches negative 2 of x, all squared. And then we're just evaluating all that. Can we just skip to the simplest form? Yeah. I'm not asking you to put all these steps. I'm just trying to kind of get you to see my logic through it. Okay, so then we evaluate each thing. So I'll start with this. Right, so the limit as x approaches negative 2 of x is just negative 2. And then we square that. So that's negative 4. Minus 1. That's what that next part is. And then we have negative 2 and minus 1. So negative 4 minus 1, that's negative 5 over negative 3, which is just 5/3. The thing I'm really worried about here is you being able to kind of split up this thing into a whole bunch of different parts. That's useful. Not necessarily all the time, but it's a good practice for their properties. That's what I'm asking. Wouldn't it be regular 4? Yes. You're right. So that'd be 3. So 3 over 3, so that's 1. Good catch. So negative 1. That should be negative 3 down bottom. So negative 1's our answer. But again, what I'm looking for is all of kind of this stuff, right? Okay, next set of directions, evaluate each limit analytically, so by rationalizing or dividing out. It's up to you to determine which one you need to do, right? It should be pretty obvious. Usually square roots kind of tell you to rationalize, or usually tell you to rationalize. So that's what we're going to do, right? In order to rationalize something, you have to multiply by its conjugate. So up here, right, we have a square root. What we would normally do is we'd plug in this limit. So it'd be rad 3 plus 6, which is rad 9, which is 3. So it'd be 3 minus 3 up top over 3 minus 3 down bottom, so we get 0 over 0. That 0 over 0 tells you that you have work to do. Okay, so you either have to rationalize or divide out. In this case, we're rationalizing. In order to rationalize, we have to multiply by a conjugate. In this case, the conjugate is going to be the square root of x plus 6, and then plus 3. And we need to multiply that by top and bottom. Okay, so when we do this, I'm going to write this out. When we multiply something by its conjugate, so a plus b times a minus c, we're just going to get a squared. That should be a b. Minus b squared. So we're going to get the two outer terms squared with the subtraction sign in the middle. And I'm going to leave the bottom as x minus 3 times the square root of x plus 6 plus 3. Okay, so when we multiply the top, square root of x plus 6 times square root of x plus 6, that's just x plus 6. Square root of x plus 6 times 3, that's 3 square root of x plus 6. Minus 3 square root of x plus 6, so those things cancel. And then minus 3 times 3 is negative 9. So we get this. I'm going to leave the bottom the same. Okay, x plus 6 minus 9 is x minus 3. So really these things cancel. And then we can take the limit of 1 over this. So then the limit as x approaches 3 of 1 divided by square root of x plus 6 plus 3. Now that's doable. Okay, so we plug 3 in. 1 over rad 3 plus 6, so that's 1 over rad 9, which is 3. And then that add in 3, so we get 1 over 9. Nope, we get rad over 6. 1 over 6. I hope that made sense. I kind of went through that pretty fast. The important part is multiplying by a conjugate, being able to FOIL, and then you're canceling stuff out. And then we're basically taking the limit of a new function. Like that was the whole idea of that lesson, is to get across to you that we're actually creating a new function that agrees at every spot but one. And in this case, we multiplied by the conjugate to do that. All right, so next one's probably a little bit easier in an example. We want to multiply this by square root of x plus 1 over square root of x plus 1. Okay, again, you could plug in 1. 1 minus 1 is 0. 1 minus 1 is 0. So we get that indeterminate form. So that tells us to do one of these techniques. Okay, so square root of x times square root of x, this thing, that's just x. Square root of x times 1, so that's plus rad x. I'm going to write all this out so we see it. Minus 1 times rad x, that's minus rad x. And minus 1 times 1, that's minus 1. And I'm going to leave the bottom just as two different factors. So then up top, we're just left with x minus 1. Those things cancel. So our new function that we're taking the limit of is 1 over rad x plus 1. So we just plug that in by direct substitution. So we do 1 over square root of 1 plus 1, which is just 1 over 1 plus 1, which is 1 over 2. Seven and 8 are going to require some factoring. All right, so if we plug in our limits here, you'll get a 0 over 0. Right, so negative 1 squared, that's 1, minus 3, so that's negative 2. Negative 2 plus 2 is 0, and then negative 1 plus 1 is 0 as well. Right, so you get 0 over 0, which tells us we have to do something. Okay, in this case, we can factor, right? We can factor x squared plus 3x plus 2 into x plus 2 times x plus 1 over x plus 1. Okay, if you need a reminder about how to do that, we need factors of our third term that add up to our second term. Right, so in this case, 2 and 1, that's 2. 2 plus 1 is 3, so those are our two factors. Those factors are going to cancel, so really we're taking the limit as x approaches negative 1 of x plus 2. If we just direct substitute that, we just get 1. Same thing in number 8. We need factors of negative 6 that add up to 1. So negative 3, or positive 2, no, negative 2, positive 3. Yeah. Again, these factors are canceling, so we're taking the limit as x approaches negative 3 of x minus 2. So negative 3 minus 2, that's negative 5, and that's our answer. Just as a kind of baseline, 1 through 8 shouldn't take you very long. My hope is that 7 and 8 are done really, really quickly. 6 and 5 have, yeah, there's a little bit of thought there, but it's really just multiplying things out. 3 and 4 is separating things, and then 1 and 2 is just a bunch of numbers. Okay, so 1 through 8 should take you maybe 15 minutes. Okay. Number 9 says determine if each function is continuous. If the function is not continuous, find the x-axis location of and classify each discontinuity as removable, unbounded, or differing behavior. I want you to use a calculator for this. Okay, so ideally you're graphing 9, 10, 11, and 12, and you're telling me where it's not continuous. There might be a little bit of algebra, maybe not number 12, but that's about it. Okay, so number 9, continuity, just as we know, continuity means that there's 3 conditions, right? So we'll say at a point x equals c. So the first condition is that f of c actually exists. The second condition is that the limit as x approaches c of f of x also exists. That should be an x. And number 3 says that these two are the same thing. Okay, so what this means, right? Number 1 just says that each point exists within some interval, okay? Number 2 says that the limit of each interval, right? The limit at some point exists at that interval. And number 3 says that the limit of that of that point is that point itself, right? So this open dot would be closed. So if you have those 3 conditions, you have continuity. Do we need to write the limit as x approaches at every step? No. I think it's good. It's good to know that that's what you're doing. You don't necessarily need to do that, though. If I'm writing a lot, normally I don't. Okay, so number 9. Number 9 is just a polynomial, right? If we think about this graph, I don't know exactly what this is going to look like, but it'll be a parabola, right? This is continuous. Every point that you plug in exists, and the limit at every point exists, and those two things are the same thing, right? So this is continuous all the time. Number 10, this is asking you to think about this piecewise function. Okay, so I'm going to graph this so we see it. Right, I'll graph the top in red. So that's x squared minus 6x plus 8 for x not equal to 1. Okay, so this is a parabola that kind of comes down and comes back up like this. Okay, where this is 3, this point is 2, and then this point is 1. Okay, and what this says is that x equals -1. We don't have 1 anymore, now we have 2. But this point is equal to 3, right? So we have a point like right here. Okay, this is not continuous at x equals 1. And this is a removable discontinuity. I hope that makes sense. Okay, so this is just the parabola part, and we're graphing that for whenever x is not equal to 1. And maybe I'll make this like teal or something. I can't see that. Blue. I'll do this. right? So x equals 2, or sorry, y equals 2. It's going to be that point right there, and that is only true at x equals 1. So we would have to pick up our pencil here so it's not continuous. And this is removable because it's just a small hole. And that's that. Okay. Right, so the limit exists here. We can approach from the left and the right, and we'll get this point. And that point exists, but those two things are not equal. Right, so if we're keeping track, right, this is true, this is true, this is not true. Number 11, this is the same thing. So if we graph 1/2 x plus 1/2, right, the y-intercept is 1/2. It's like right here. We go up 1/2. So up 1/2. And this is true when x is less than or equal to 0. So this is true for everything over here. And then we're going to graph the line negative x plus 2. So negative 1x plus 2. So our y-intercept is 2. It's like right here. We go down 1, right 1. And we're worried about that for when x is greater than 0. So we're over here. And really this is a filled in circle. Or not a filled in circle. Okay. This is not continuous at this point x equals 0. It's not continuous because of different behavior. So not continuous at x equals 0 because of differing behavior. Hi, Mateo. This is not scary. This is just 2 lines in one. Number 12, same thing. We know that this is not continuous at x equals 2 because when we plug in x equals 2, we're either going to have an asymptote or we're going to have a hole. So what I'm going to do is I would graph this, and when you graph this, you get just a straight line, okay, with a hole, right? So you're going to get a straight line that looks kind of like this, okay? But this can't be continuous at x equals 2, right? So there's going to be some kind of hole like right here. And the reason being is because our denominator is here. Okay, so if we think about this, we would have negative x plus 3x minus 2 over x minus 2. So these two things will cancel, and we'll have a hole at that place. So this is not continuous at x equals 2. And this is a removable discontinuity. Okay, so really for 8 to 12 or 9 to 12, we have to think about the domain of all these things and see where they don't match up, right? So like number 12, the domain is x can't be 2. So you either have unbounded behavior there or you have a hole, and you have to figure out which one. For number 11, you have differing behavior. Graphing that will help. Okay, graphing all of these will help, except for like maybe on number, well, it'll help on everything. Okay, just as a caution, the only thing we didn't cover here is unbounded behavior, so that might show up on the actual test. Okay, so that's 9 to 12. Number 13, it's just asking you to plug in really close numbers to -4 on the right, and numbers really close to -4 on the left. Okay, this is kind of like number 1 and 2. So like let's plug in, well, let's think about this first, right? We have x minus 4 over x plus 4, x minus 4. So we're not worried about these two things. Those two things cancel. And we're worried about what happens at 1 over x plus 4 as we approach -4 from the right. Okay, so we're going to plug in something really close to -4, but on the right of -4. So like let's look at 3.9. And when we do that, we get 1 over 0.1, which is 10. Right, so this tells us that when we go closer and closer to -4, but on the right, we're going to get bigger and bigger numbers, right? So if I did -3.99, I'd get 100. If I did -3.9999, I'd get 10,000. Okay, so this tells us that our limit is going to positive infinity on the right. Okay, and that should make sense because this thing is always going to be positive when x is less than 4. Or when x is greater than -4. Same thing over here, right? We're worried about the limit as x approaches -4, but now on the left. So now we're worried about 1 over x plus 4. But we're going to plug in like -4.1. And when we do this, we're going to get 1 over -0.1, which is going to be -10. And this tells us it goes to negative infinity. Graphing this is also going to help, just like pretty much everything else on this test. So if we graph x minus 4 divided by x squared minus 16, we get something that looks like this, right? So as we approach -4 from the right, we're going up to positive infinity. When we approach -4 on the left, we're approaching negative infinity. I hope that makes sense. Okay, this is just looking at graphs and really seeing what's happening on the left and the right. Okay, 15 to 17 is what we kind of covered. This is like the last bit that we covered, or one of the last bits that we covered. And this is basically just asking you what's happening as we approach positive infinity or negative infinity. So when we go super far right on the x-axis or super far left, right? So this, I know you probably can't see this on screen. This says as x approaches negative infinity. So what we have to think about is which one of these things grow faster. Okay. And really all that matters here is the degree of x. Okay, because when we're getting really, really, really big, constants don't matter. So we are not worried about this -3. We're not worried about this 1. We also have x squared in the denominator. And in terms of like x squared with really, really big numbers, this 2x doesn't matter either. So we're just focused on what happens with -x over 2x squared. So the only thing we're worried about here, I'm not going to say equals because that's not true. We're only really worried about negative x over 2x squared. And what grows fastest, right? So in this case, x squared is going to grow way faster than x, especially with really, really big values of x. Okay, so this is getting bigger faster. So if our denominator is getting bigger faster, our entire fraction is going to 0. So this thing is going to go to 0. And the negative really doesn't matter. It would matter if it wasn't going to 0, but in this case, it doesn't. Okay. Number 16, the limit as x approaches infinity of x cubed minus x squared minus 1. In reference to infinity, this negative 1 doesn't matter at all. In reference to cubed, this x squared doesn't mean anything at all. So basically, we're taking the limit as x approaches infinity of x cubed, which is just going to be positive infinity. Number 17. Number 17 says the limit as x approaches negative infinity of negative 3x squared over x squared plus 4. So let's kind of break this down. This positive 4, right, in terms of infinity, 4 doesn't matter, right? If you're negative trillions of dollars in debt, $4 isn't going to make much of a difference. So we're really looking at negative 3x squared over x squared. These x squareds are going to cancel, and we're really just left with negative 3. So our answer here is just negative 3. And I'm going to double check that just to make sure, but I think that should be right. Yeah, that's right. And again, graphing this is going to help. You get a graph that kind of tends toward negative 3 as you get way further away from x equals 0. Easy money. Yes, it is. Mateo, this is the same thing we did with graphing rational functions. It's just using the limit definitions of stuff instead of like the actual rules, I guess. Okay, so that's that part. Number 1, on this next part, for each function, identify the holes, vertical asymptotes, and horizontal asymptotes. So whenever you're doing this stuff, the first goal is to factor. If anything factors out, that's a hole. At the very end, can you go through a similar problem of 10 and 11 slowly? Yes, I can. Hi, Mason. Number 10 and 11, I just want to see what that is. Yes, I can do that. Okay, so holes are anything that factors out. Vertical asymptotes. So after you factor all of that stuff out, you set the denominator equal to 0. And horizontal asymptotes is where you compare the degrees of the numerator and degrees of the denominator. But what you really need to know for horizontal asymptotes are the problems that we just did. So if you know that, you don't really even need to know these rules, but I'm going to write them just in case. So if n is less than m, so if the degree of the numerator, that's what n is less than the degree of the denominator, that tells us y is equal to 0 is our asymptote. The rest, Mateo, you've done 1 and 2. You literally, I just tested you on this. If n is equal to m, we get the ratio of the leading coefficients. So I'm going to write an over bm. If you don't know what that means, that's the thing attached to the highest power of x in the numerator over the thing attached to the highest x in the denominator. And if n is greater than m, there is none. And again, you know these if you know the things that we just did up here. Okay, so that seems like a lot, but it's really not. It's the same thing. Okay, so for part one, I want to factor the top. I want to see if I can factor the top, rather. So I'm going to take a negative out first. Okay, so I can factor the numerator as x plus 4, x minus 2. And then I can factor the bottom as x plus 3, x minus 1. Okay, so nothing cancels out. So there's no holes. So for vertical asymptote, you just take that denominator and set it equal to 0. And vertical asymptotes tell you where you get that unbounded behavior, right? So if we just set x plus 3 times x minus 1 equal to 0, we have a product of two things equaling 0, so one of those two things has to equal 0. So either x equals negative 3 or x equals 1. And those are vertical asymptotes, okay? And then a horizontal asymptote is basically asking the limit as you approach infinity. So I'm going to look back up here, right? We have x squared and x squared for the numerator and denominator, so nothing else is going to matter. Okay. When we take the limit as x approaches infinity of negative x squared over x squared, we're just left with negative 1. So that's going to be our horizontal asymptote. Again, there's nothing crazy difficult. It's been this is doing things we've been doing all along. Okay, we've been setting the denominator equal to 0 to find the domain, and we've been taking limits as x approaches infinity, which has to do with horizontal asymptotes. Okay, this is just putting it kind of in different language. For number 2, we're going to do the same thing. So I'm going to try and factor out the top. There's a common x factor up top, so I'm going to pull that out. And I can factor that into x times x minus 3, x plus 2. On bottom, there's a common negative 3, so I'm going to pull that out. And we can factor that as x plus 4, x minus 3. Now, we can take out x minus 3 and x minus 3 from the top and bottom because those are common factors. So because we do that, we have a hole at x minus 3 is equal to 0, so x is equal to 3. We have vertical asymptote when the rest of the denominator is equal to 0. So at x equals negative 4. And then for horizontal, we're worried about the degree of the numerator and denominator, right? So if you look at the degree of the numerator has an x cubed. For the denominator, we have an x squared, and literally nothing else matters. Okay, so if we take the limit as x approaches infinity of both those things, x cubed is going to grow way faster than x squared. And because of that, the numerator is going to grow faster than the denominator, so our entire fraction is going to infinity. Right, so in this case, there is no horizontal asymptote. And again, the reason is because if we take the limit as x approaches infinity of that function, we just get infinity, right? The numerator is growing faster than anything, so our entire fraction is going to infinity. So that's 1 and 2 on part 2. And then we have kind of the thing that I made. All right. So using the graph above, answer the following questions. I'm going to make this smaller if I can. There it is. Okay, so use the graph above to answer the following. So first thing says f of 3, right? So we plug in 3 into the x value. And that's going to tell us our answer, right? We're not worried about open circles. We're only worried about closed circles. So f of 3 is equal to 6. The limit as x approaches 3 of f of x is what happens as we approach x equals 3 from the left and the right. Right, so we're approaching on the graph from the right and the left. And when we do that, we're approaching this value right here. So 4 is going to be our answer for that. Limit as x approaches 5 from the left. Okay, so we find 5. Okay, and we're approaching that thing from the left. So on our graph, we are approaching from this direction. So from the left, we are approaching 7. Okay, so just in case we can, so this is limit as x approaches 5 from the left of this function. So on our function, we are approaching from the left. And if we do that, we're approaching 7. Approaching 5 from the right. So I'll do this in this color. So now we're approaching from this direction. So on our graph, we're approaching this value, which is 3. Okay. Limit as x approaches 12 from the positive side. So we are approaching 12 from the right. So on our graph, we're going up. And there's no stop point, so we're just going up until infinity. So the limit as x approaches 12 from the right of this function is just going to go to positive infinity. Label and classify all discontinuities, removable, different behavior, or unbounded. Okay. So I'm going to kind of talk about this because going back and forth between them. I'll do this in highlighters. First discontinuity is right here. Right? We have this open circle in it. I'm going to make this better. Come on. Okay. First discontinuity is this hole. If we were drawing this graph, this would be the first place where we pick up our pencil. Okay, so this blue, that is a removable discontinuity. So a hole is just a removable discontinuity. Okay, so x equals 3, removable discontinuity. The next part where we'd have to pick up our pencil is right here. And once we pick up our pencil, we move all the way down here. And as you could tell from our answers here, the limit from the left and the right are different. So this would be x equals 5 is our discontinuity, and then this discontinuity would be different behavior. X equals 8, that's just another removable. And again, when you're doing this, I'm expecting this to be on the bottom of the page. This is too big to be scrolling down. So all this stuff would go down here. Okay. But that's what's happening. All right. The other one is x equals 12. Right, so this is, right, we're going to positive infinity on both ends. So this is unbounded behavior. And that's the test. Okay, so this last page should be relatively straightforward. It's just asking you a bunch of different questions about a graph. All right. The rest of the test is, most of it's just like evaluating limits. Right. So I'm going to start from the top. I'm going to mute myself and make sure there's no questions, but I'll kind of slowly scroll through the test. If there's no questions within the next, let's say 3 minutes, then I'll close it. But as you have questions, ask, and I'll try and answer them before people leave. Okay, so I'm going to scroll back up to the top, slow scroll down, and then in the next couple minutes, I'll end it. Also, I know I still have to do a piecewise function. I just thought of that. I'll scroll through it first, and then I'll do it. Would 8 be positive 5? No. Negative 3 minus 2 is negative 5. Okay. I want to do one more piecewise function just so people see how to graph it. Yeah, I'm getting there. I'm going to kind of regenerate one though, so give me like 2 seconds. All right, 2 seconds. Okay. I'm going to change this to 1. No, I'm gonna make this 2 again. If it's a piecewise function, is it automatically a discontinuity? No, it is not. I could come up with different functions that meet up at like the bounded stuff, like so this stuff. It doesn't necessarily have to be like they can meet. They don't have to be apart. Right? So before I get onto this example, I could make a piecewise function that's like a parabola over here. And then, right, so that's a parabola for when x is less than or equal to 0. And then I could make a straight line. That's the line y equals x plus 1 at x is greater than 1, or at greater than 0, right? So that is continuous. But they can be split up, and that's where those discontinuities come into play. Okay, so let's do this example. Oh, shoot. No, all right. All right. So piecewise functions. Piecewise functions are just 2 functions in one with specific domains, right? So the domain of this top one is for x is less than or equal to -1. the domain for this bottom one is x is greater than negative 1. Okay, so we have this parabola whenever x is less than or equal to negative 1. And we have this line when x is greater than negative 1. Okay, and that's literally all it is. It's two graphs in one. So x squared plus 2x plus 2. I'm just going to look at what that looks like on a graph so I don't have to think about it. X squared plus 2x plus 2. That is a graph that at negative 1 has its vertex. It kind of comes up like this. And it goes back up and passes at 2. Right, so that's the graph x squared plus 2x plus 2. I'm going to get rid of this stuff and I'll work in colors. Right, so all I did was graph this part right now. All right, that's that graph. But then what I need to do is I need to think about this domain. So this graph is only true for x is less than or equal to negative 1. So I find negative 1. And I delete everything to the right of it because I'm only worried about when x is less than or equal to negative 1. So I'm going to erase this piece right here. Now it's less than or equal, so this is going to be a filled in dot. And that's right now, that's the first half of our graph. For this other graph, which I'll do in like teal, negative x plus 2. Right, so this says we have a y-intercept at plus 2. And we're going to go down 1, right 1. So really down 1, up 1, but... Or, sorry, up 1, left 1. So we're going to have a point like right there. So then this is the graph of that second part. Okay. And this is strictly greater than negative 1. So we're only worried about this piece that I drew. And we're going to have an open circle right there. Okay. This graph is not continuous at negative 1. Because there's different behavior on both sides. Okay. Again, it doesn't have to, so normally the discontinuity is going to happen here. So at x equals whatever that value is. In this case, x equals negative 1. But it doesn't necessarily have to, right? So I could write a function that looks like this over here, and it's totally continuous. The problem is when things don't match up, like I have in this problem, okay? So I does that make sense? I hope that makes sense. I'll give you a second to look at it and think about it. Perfect. Okay. This has been long. We're on here like an hour and 20 minutes. So I'm going to keep this open for another like 2 minutes, let's say. And if there's no questions by then, I'll call it. All right. So I'm going to mute myself. If you have questions, just post them and I'll try my best to respond to them. Can there be unbounded behavior in a piecewise function? Absolutely. Am I going to do that to you? No, I think that's combining too many things at once. But there can be. I mean, I could easily write. Uh, this is off to the side, so don't worry about this. Don't let this confuse you. But I could write a function that looks like 1 over x for x is greater than 0. And then like the line negative x plus 2 at x is less than or equal to 0. This part right here is going to be unbounded at 0. So our graph is going to look like unbounded over here, and then it's going to be like a line right here. I guess the top part will be in green, the red part will be the red part. Make it look better though. All right, so that red part is linear, that green part is the reciprocal function that has unbounded behavior. I can make any graph I want piecewise. It's just patchworking a bunch of functions together. Okay. It doesn't seem like there's any more questions, so I'm going to call this now. Again, if you need a fresh version of that, rather of this, all of this, it's in on campus. It's in that chapter 1 material. And hopefully this was a good explanation for most of it. All right. If you have questions, let me know. I'll try my best to answer them. But yeah, so that's all I have. Good luck tomorrow, and I'll see you tomorrow. All right. Thank you guys.